Uh, we'll take some examples to mm, examples in order to study robust stability against unmodeled dynamics. So we'll assume, as I said, we'll assume that controller you have designed, and we'll just post check whether the controller how much mm, uncertainty the controller is able to tackle. Okay. So, so we'll start with very simple plant, and this kind of plant uh, is very practical. This is a delayed plant. This is a e to the power minus tau s divided by s square. This kind of this transmission delay occurs. Maybe nowadays all the controllers are digitally implemented, so there is a communication delay, there is a computation delay. Okay, so there is this delay is unavoidable nowadays. uh, uh, Nowadays even this these plants are controlled in process industries. Plants are controlled, controlled over networks. Okay, so network delay, that means control signal, signal from the sensor to the controller is transmitted through a communication wireless, maybe wireless communication network, and similarly from controller to the plant, the actuating signal is also transmitted through wireless sensor network. So nowadays those kind of advancement are slowly being made in process industries at least. Uh, so this kind of delays are time delay is unavoidable. And if it is a delayed plant, okay, there are some process plants which have delay, inherent delay is inherent to the system. So so such kind of plant we have considered is a simple second order double integrated plant, okay, but with delay. So naturally, we'll design the controller ignoring the delay, right? So the controller will be designing for this plant, second order plant, ignoring the delay. So the question is, suppose a PD controller, although PD controller is not taught yet, but I think you will not face a problem. PD controller, all of you know, it's the KP, the controller transfer function is KPS plus KD into S, KP plus KD into S. So suppose a PD controller is designed for GS to place the closed loop poles at S equal to -1, -2. Okay, so how PD controller can be designed to place the poles at S equal to -1, place the closed loop poles at S equal to -1, -2? That we'll see. It is not difficult at all. Okay. So now the main thing is that you have suppose designed some controller, uh, and then what you have to do, we have to verify, as I said, we'll post check now. Determine the amount of delay tau that the closed loop system, that the feedback system can tolerate. That you have to find. So one way to handle this problem is also using the concept of delay margin, but we'll handle this problem from the concept of robust stability against unmodeled dynamics. Robust stability condition against unmodeled dynamics we will use to obtain the condition. Okay, so here only I have considered this delay, neglected dynamics. So delay we have neglected, the neglected dynamics. It may have some other higher order dynamics which we have neglected. It may have, we may consider, but we have considered delay. Okay, so now, so this is the question. So how will you proceed? So first we will find what is the normalized error. So normalized error is what? G hat by G minus 1 equal to G hat by G minus 1. You can easily see G hat is this, G is this. So G hat by G is this, okay, minus 1. So this e to the power j theta, you can write like this, cos theta plus minus cos theta plus j sin theta. So minus is there. So that's why cos theta minus j sin theta minus 1. So this you can simplify, cos tau theta square minus 1 plus sin square tau theta. And this is equal to, you can simplify it to be 2 into sine of tau omega by 2. Okay. So this we have, this simplification we have made. So this is your normalized error. So now what is the next step? The next step is we'll plot the normalized error. So if you plot the normalized error, this is your frequency response of normalized error, EA j omega by G j omega. The frequency response of normalized error will be this one. Right? This is your frequency response of this 2 sine tau omega by 2. So this magnitude is 2, okay, and this is the your sine, because mod is there, okay, so that's why it is positive. Okay, so now what is the designer tax? What is the, how will you verify? Now I have to consider a WCS, that means weight, uncertainty weight, which will encompass the uncertainty. So you can see the uncertainty is, as I said, the uncertainty can be of any shape. It is not like it, and the shape of the uncertainty is like this. You can see now the uncertainty is of not of peculiar type of shape. This is the frequency response of the uncertainty. Okay, so it may have. So now we have to consider a WCS which will encompass the uncertainty. So I have considered a WCS. So in order to have less conservative bound, our WCS should be chosen as tight as possible. That is the designer task. So I have considered, suppose WCS, as WCS obviously a high pass filter. So the high pass filter I have considered like this. Your WCS equal to Ks by Ts plus 1. This is a first order high pass filter. Okay, it may happen that for my case it is first order will suffice. It may happen the uncertainty is such that you cannot get a tight weight using first order. You may have to consider second order weight or so on, right? It doesn't matter. So I have considered first order weight here for simplicity, and in fact first order weight can encompass this uncertainty. So this is a high pass filter, high pass weight. You can easily see the WC infinity value, that as the omega, as omega tends to infinity, or the yes, the steady value. So value is k by 2. So this value. So but the steady value of the error plot of the normalized error is 2. So that's why what I have chosen, I have considered this steady value of WCS. I considered it to be 2.1, so that it just encompasses, it just lies above uh, no, this peak value of 2. So k by t I have considered as 2.1. Okay, so for that k will be equal to, then k will be equal to 2.1 into t, and from the figure what we can get. So WC omega c is what? Omega c, that means cutoff frequency. Here this cutoff frequency is 1 by t. Okay, this is your 1 by t. So 1 by t. So cutoff frequency is your what is tau here? 2 point what is this tau? Okay, this slope is, you can see, this is your uh, this this cutoff frequency, this corner frequency is omega c. So this slope is, so here to here is omega c, and here and this distance is your 2.1. Here to here is 2.1. So 2.1 divided by omega c. 2 point divided by omega c. This will be equal to tau, or you can write omega c equal to 2.1 by tau from the figure. So this slope here is into tau. Okay.
Sir, how is that slope tau?
This is your theta. The tan theta equal to WC divided by tan theta equal to what? Tan theta equal to 2.1 divided by WC, right?
Yes.
So this slope tan theta I have taken as suppose tau.
Sir, this tau and the time delay tau are different, or are they the same?
And different. Oh, this tau I could have used some different here. Anyway, this tau will not be used later. Okay, this tau will not be. This is just for our understanding. I have denoted. So better I could have written this as tau one. That I will rectify. Okay, so this tau is different from time delay. You are correct. You have correctly pointed out. This tau is not this tau. Okay, so your this slope, this slope. No. This is tau, because if you no, this tau is same, because if you take derivative of this one, this error, what will be the magnitude? What will be your slope? What is the slope of this one? If you take derivative of this, what is the slope of this function? This is what is the slope? Tau into omega, right? What is the slope? The slope is tau, right? For this one, what is the slope?
Yes, sir, it's tau.
Tau. So this tau, that tau are same. Sorry, this tau and that tau are same. The slope is tau. Okay. So that's why this is 2.1 by tau. So now we suppose we will design the PT controller. Okay. So this is a second order system. So as it is a second order system, we will see that PD controller can achieve pole placement, complete pole placement. So up to this, I think is clear now. So how will you design PD controller? So you can easily find it. Say you can easily check that your closed loop pole polynomial will be 1 plus gs into cs. Cs is your controller, is equal to 0. So what is your gs? 1 by s square. What is your PD controller transfer function? PD controller transfer function is kp plus kds equal equation, right, with PD controller. Okay. So now what is there in the question? In the question it is there, I want to place the poles at -1 and -2. So then what is the desired closed loop pole polynomial? Desired closed loop pole polynomial is s plus 1 into s plus 2, right? That means s square plus 3s plus 2 is your desired closed loop pole polynomial. Then how to get this desired closed loop pole polynomial using KPKD? Just you equate this s to the power 2, s to the power, these two equations if you equate, then what will you get? KD will be equal to 3 and KP will be equal to 2. Okay, with that you will get this desired pole point. So that system you can stabilize using Kp equal to 2 and Kd equal to 2 in order to have the pole locations at s equal to -1 and -1. Got it? So if this is the case, now we have to post check whether robust stability condition is satisfied and for what value of tau. So what is the complementary sensitivity function here? Complementary sensitivity function is Ls divided by 1 plus Ls, that means Gc, Gc divided by 1 plus Gc. So what is your G? G is 1 over S square. What is your C? C is this divided by 1 plus C into G. So that means this is equal to this. If you substitute the KPKD value, it will come out to be this. So now for robust stability, what is the condition? T j omega plot should always lie below 1 by WC plot. Now what is 1 by WC? We can see 1 by WC is what? Ts plus 1 divided by Ks. Okay. So Ts plus 1 divided by Ks. Now you have to plot first Ts. Ts is fully known because controller you have designed. So Ts, so I have considered this example very simple so that you can plot by hand. In fact, board magnitude, asymptotic board magnitude plot I have made, I have drawn here. You just check. I think you know asymptotic board magnitude plot. If you do not, if you cannot remember, please brush up those things because these concepts will be very much needed in design course. Asymptotic board magnitude plot. Okay. So this is your omega, okay, in log scale, and this is your linear scale, not in dB scale. I have not drawn in dB scale, but this is your in log scale. Okay, so you can see what are the cutoff. You can see here 2 by 3. So this one, this is a zero polynomial. So this 2 by 3 cutoff frequency, cutoff frequency is 1. Okay, and this is 2. Okay, and 3 RML. So here the slope is positive because of this zero location, and then again this slope becomes 0 because of this pole, and then again it goes to downward because of this one. Okay, so like this, and you can easily verify that this is in case of dB scale it is 0 dB, but it is linear scale, ES scale, that's magnitude scale. So this is just 1 instead of 0 dB. I have written here 1. Then what is this magnitude? Just 1 divided by 3 by 2, 2 by 3. 1 divided by 2 by 3, that's why it is 1.5. Okay. So now what is the base? What is the tight bound of tau? So to achieve that, as I said, that your T omega plot should lie just below 1 by WC omega plot. So 1 by WC omega is what? So here T equal to 1 by omega c equal to tau by 2.1, and k equal to, we have already seen that k equal to 2 into tau, right? 2.1 into t. So that means all these values k as well as t we can represent in terms of tau. This k by t equal to 2.1. Okay, so this k and t we can represent in terms of tau. So if you plot it, if you plot this transfer function, so it will look like this. And then what is this corner frequency? Corner frequency is obviously 1 by t. Okay, 1 by t equal to 2.1 by tau. So now, so your Tj omega plot should be just below this plot. So that's why I have drawn this 1 by WC omega just above this this plot. Okay, and you can see this is possible if so. So if this is the case, then what should be your 1 by t? So so this line touches this one, and this magnitude is what? 1 by 2.1. You can easily see this magnitude is t by k. So t by k is k by t is 2.1. So t by k, this magnitude, this magnitude, this magnitude is t by k. So that's it is 1 by 2.1. Okay. So if it just touches, then this point is 1 by t. Okay. So if it just touches, this is 3 and this is 1 by 2.1. So then what will be this point? This point is 6.3 radian per second. So that means in order to guarantee robust stability over 1 by t, 1 by t should be just greater than 1 by t should be just greater than 6.3. Okay, so that I have written. So 1 by t for robust stability 2.1 by tau should be just greater than 6.3. It will so in order to guarantee this, the tau should be less than 0.3 seconds. Okay, so have you understood? This is very important example. Okay, you will not get these examples in books. I am telling you. Okay, so so I have framed this example and I have verified. Okay, in another book is there. One is Feedback Control Theory by Francis Tannenbaum. Feedback Control Theory by Francis Tannenbaum. So there, partial, a small part of this example was considered, but only they have done that this can be expressed, this omega c and all these things they have chosen. Then they stopped. Okay, but I have extended this problem in order to use this robust stability condition. Okay, so in this way you can. So if you have any doubt, please tell me, because this kind of problem I'll in this weekend I'll give you an assignment. Okay, so there are many problems. This kind of problems I have. I'll give you. Okay, I have made it. Okay, so if you have any doubt, please tell me. Okay, so only thing is this one, you have to draw the board plot properly. It's a board plot of the complementary sensitive function. Okay, you can see the complementary sensitive peak is 1.5. And as I said, with PD controller, you cannot get minus 40 dB roll-off rate. What is the roll-off rate here? Minus 1 slope. That means minus 20 dB per decade. That is the disadvantage of PD controller. If you use some other controller, you may get better. You will get better tau. Okay, so with PD controller, this slope is called your 20 dB per decade. So high frequency roll off rate is only 20 dB per decade minus with other controller, because so this roll off rate reduces because PD controller is an improper controller. So it reduces the relative degree of the loop. If the controller, although you can easily see, if although the controller plant relative degree is 2. Plant relative degree is 2 here, 2, but the controller is improper, Kp plus Kds. So that's why your loop transfer function relative degree becomes 1. So because of that, your high frequency roll off rate, that means if you plot the loop, or if you see the roll off rate here, Okay, complementary sensitivity function, and the roll-up rate your becomes minus 20 dB per decade. Or if you plot the loop transfer function, then also you'll see the high frequency roll-up rate here minus 20 dB per decade. Hello? Okay, so we will consider another example. So now we'll consider some unmodeled. So this example also I have taken from the exercise of that Francis Tannenbaum book. That is feedback control theory by Francis Tannenbaum. Okay, so here here also the true plant is uh, like this. You can see a true plant is this one, and this is your unmodeled dynamics, and your, as I written, suppose a proportional controller CS equal to K is designed for the approximated plant GS. So G 1 by S minus 1 we considered as an approximated plant. Okay, and you design a proportional controller because for this plant is a first order unstable plant. Proportional controller suffices, and you designed a proportional controller for this, and the objective is to find the range of gain K such that the true closed loop system is stable. True closed loop system means I have designed controller for the approximated plan, but true closed loop system has this one as unmodeled dynamics or neglected dynamics. So even if the neglected dynamics is there, then you have to find what is the range of gain K which will make the closed loop system also stable. So here, what is your WC? WC is this one. You can easily see 0.2s divided by s plus 10. Okay, and this is equal to 0.02 divided by this, and TS, that is complementary sensitivity function, is K by s plus K minus 1. So what is the condition? Your here now WCS is known. You have to determine K such that Tj omega plot will always lie below 1 by Tj omega plot will always lie below 1 by WCj omega plot. Okay. So what will be your Tj omega plot? WCj omega plot. So you can easily see this is your 1 by WCj omega plot, right? This is your cutoff frequency is 10, 1 by WC. Remember that. So WC is a high pass filter. Just flip it. Uh, so if you plot WC, the response will be like this. Just I have flipped it. 1 by WC. Okay, 1 by, so this is minus 1 slope, minus 20 dB per decade, and then 0 dB per decade. Although here I have used the linear scale, not dB scale. Here it is log scale. Okay. So this magnitude you can easily see from here. This magnitude is this this magnitude. This magnitude is 5. And here 1.1 divided by 0.02. So 0.1 divided by 0.02 is 5. Okay. So now what is the plot of K by S plus K minus 1? Plot of K by S plus K minus 1 is like this. Okay. Here again it is minus 1 slope or minus 20 dB per decade, and this is 0 dB, 0 slope, and this point is this magnitude is K by k minus 1. And what is the corner frequency? Corner frequency is here 1 by k minus 1. Okay. No, corner frequency should be k minus 1, right? Why 1 by k minus 1? Corner frequency is k minus 1. So I have written wrongly here. Corner frequency is k minus 1. Sorry, I will correct it. Corner frequency is k minus 1. Okay. So corner frequency is here. Corner frequency is k minus 1. Uh, so I have got a so it is obvious that if uh, you may try to find more tight bound, but I could not. But just uh, that robust stability can be guaranteed just if this plot lies above this plot. To have that, uh, just you can easily see that k by k minus 1, if this one is lies always below this 5, then you can always achieve. So that I have made k by k minus 1 is less than 5, which will uh, need k greater than to 1.25. Okay, you may try to find some more tight bound, but I could not. Okay, that is your task. If you can find out some more tight bound, you may tell me, but I think you will not be able to find. Okay, so k should be greater than 1.25, and interestingly, you can also see that k greater than 1 is needed in order to make it nominally stable. Even that also you should keep in mind when you will obtain more tight bound. Okay, so the in sufficient condition for robust stability. This is a sufficient condition. This is a tight bound. More tight bound. This is not the exhaustive case. More tight bound you may be able to find, but uh, I tried. I feel this is the most tight bound for this problem. Okay, so this kind of problems you have to solve. And again I am saying that these are all post checking. We are not designing robust controller. We are checking the robustness of the system. Okay, if it is a simple system, like as here it is a proportional gain, right? We have to find that, this you can say it is a synthesis kind of thing. But in the earlier case where you have designed PD controller, and then we checked post checked the robustness against uh, uh, delay, right? Delay range or delay bound we have found out for which the closed loop system will remain stable. So in this way, given a practical system and a controller, you have to determine that what range of uncertainty bound it can tolerate. Your design controller can tolerate, right? So if the uncertainty bound is known to you, and the uncertainty plot you can get following that method, as I said, g minus g hat, right? That error plot you can get for any plan. And once you get that plan, and then you can easily find out, easily verify at least whether your design controller can uh, tolerate the uncertainty or not. At least that much uh, you should verify, okay, before employing the controller for a practical system. Okay, so I'm stopping today. If you have any doubt, you can ask me.